This is the last lecture, and actually what I'm going to tell you today is in about at least 2, but maybe 2.5 of the papers in that booklet. It's about another type of, I mentioned at the very beginning in my introductory lecture, another type of random walk or diffusion with long memory. And here the long memory doesn't come from a random environment which is fixed from start, but the random environment is somehow built up by the random walk itself. So it's a joint dynamics of environment and the random walker, or diffusion in RD. That's what I will speak more about. In the following way, I will explain it in a moment with pictures. Just to explain, so I chose to find some old slides about this type of thing because time is short. This is a shorter lecture, and it's too much to say, so I decided better. So if you want to, I tell you which papers it is about. Just I don't have which papers. Yes, that's the first one which appears there. Unfortunately, there are no page numbers in this booklet. So if you go towards the second half, say last third, there is a paper, Diffusive Limits for True Self-Avoiding Walk, and so on. There is a next paper, Diffusivity Bounds for One-Dimensional Brownian Polymers. And there is half of the paper which is super diffusive bounds for self-repellent Brownian polymers. So these 3 papers, one after the other one. It's not the case that I will follow now one of these papers, and probably the notation will also be somewhat different, but probably it will be self-contained, or at least I plan to have it self-contained. Okay, let's jump into it. So I'm interested in random walks on the lattice or diffusions on RD with the following property. I'll tell you in plain words first. A random walk which has long memory due to the fact that it doesn't like to go back to places where it had been much in the past. So it models some, if you want, motivation from some science, then probably biological motivation is the best, namely that this is in biology is called negative chemotaxis, when a population is dispersed due to the fact that, okay, they live too much in a place, they eat up everything which was edible there, and they have to go to other places to eat. But at the same time, they walk diffusively, randomly, but they have this push away from locations where they had spent much time. Now this is about, it's very clearly, just I have to learn how to use this, yes. It's very clearly explained. I think I speak about a random walk on the integer lattice ZD. On this slide, you will have with discrete time, define its occupation time measure on the lattice sides. That means that at time n and position x is on the lattice side, n is a time of n is time. Let's say you have some initial values which will have some importance later, and otherwise it's adding, so the change after the initial value is just the occupation time. So how many times it had been to that particular site. So these 2 random processes are related, of course. You can, if I give you the trajectory, you can compute this as well. Take your favorite increasing function from the integers to the positive reals. Let it be increasing. And I define my walk. The law of the walk is the following. Given the whole past, so it's non-Markovian, I have to know the past of the walk in order to determine what is the jump probability in the next step. In particular, in this past information, of course, it's there that where the random walker is at this particular moment. The next step is distributed, so y is a neighbor, is one of the neighbors, and it's distributed according to this function, which looks complicated, but it's not. Take this increasing function, take the gradient, actually the negative gradient of the occupation time measure, insert it, put it into this increasing function, and your jump probability will be proportional to that. So it chooses one of the neighbors according to where is this gradient, how should I put, the least, but in negative it could be the maximum. So it tries to jump to those places where it had been less in the past. Particular examples of WR could be chosen, exponential or negative exponential or other things. Anyway, so for the moment, let me just stop here. Next, I will give you a number of models like this. The next one is just a variation of this one. It's in continuous time, and I will jump very fast. So this is just a continuous time. Walk time is continuous. Again, it's occupation time measure. Now it's a continuous, time is continuous. So this is a positive real or non-negative real number. Now I take my rate function increasing from the reals to the positive reals. I impose a lower bound on this. For some reason, I will separate I did it in the random walk case. Remember, I separated the symmetric and anti-symmetric thing. I again separated the anti-symmetric part of this function from the symmetric part of this function. And now I say, this is just for the future, notation for the future. And I say that my jump rates now are proportional to this W of the negative gradient of the occupation time measure. Is it clear? Right. Question?
So this one W doesn't need to be increasing?
Didn't I say?
Well, you said that R.
I said R increasing. Actually, R increasing is sufficient. Okay. That's R increasing. R is the odd part of it. Of course, if W increasing, then you easily see that R is also increasing. So this is a weaker condition than W be increasing. You can have W not strictly increasing. Intuitively, you think that the phenomenon I spoke about is with W increasing, but in the proofs, it will be enough to have R increasing. Good. And the last one of these, this is just the sister of the other one. The last one is continuous space. So it's a diffusion, which does about the same thing. So I define a diffusion here. This will be a bit tricky to define because you have to take care about existence of the process. In the previous cases, there was no problem of the existence. But here, that's not a big deal. So I think about a random process, continuous time, continuous space, and it will have continuous trajectories, so it will be sort of diffusion. I denote its occupation time measure. It does make sense. If xt is, say, continuous path, then it does make sense as a measurable object. This occupation time measure, at least, occupation time measure, define it on open sets and then extend it as you extend measures usually. What do I want to say here? Yes, choose a function. Here it will have absolutely importance. That's why it's denoted by a red star here. That I choose a function which will be a smoothing function as it was yesterday or the day before yesterday in the case of that diffusion in random environment. I have to smooth out local times, otherwise it doesn't make sense. So this be something which has positive Fourier transform, very important, of positive type, that's how we call it, or that's how Bochner calls it. So a function of positive type, I prefer to think in concrete terms, so take this one, for example, that's perfectly good. Assume it decays, V decays fast, exponentially fast, faster than any polynomial. It's infinitely smooth so that we don't have any technical problems. And I'm not done yet. Define the negative gradient, take the negative gradient of this function f. This is just notation, right? And now I define my process in terms of a stochastic integral differential equation. I have three equivalent things. For me as a physicist, I mean in heart, the last one makes most sense because that tells you the phenomenon, but it's equivalent to the previous ones. For mathematicians, maybe the previous ones are less. The first one looks less singular, so that's more attractive. Let me speak of the last one. So it's a diffusion whose infinitesimal increment is given by a Brownian motion, by a noise term, and take what? Smooth out the local time, smoothen it out but by convolving with this e to the minus x squared to have a function which makes sense. This will be, if you smoothen it out, it will make good sense as a continuous object. Take the gradient of this function. So this is like the density the local time doesn't have density. It's a very singular measure. But if you smooth it out, then this object you see here is an approximate density of the occupation time measure, right? Take the negative gradient at the position where the random walker is, and that's the drift. So the phenomenon is exactly the same, just it's in continuum. You have a diffusion, it tries to diffuse, but on the other hand, it has a push towards local push, doesn't see far away. You have to keep in mind, in memory, all what happened, but when you locally decide what to do in the next second, you don't have to look far away, right? Good, and the phenomenon is exactly the same, that it's pushed away. Good, so this is the type of processes I want to consider. And here is some sort of history of the story, which is very interesting in my opinion. Don't have to write down the names. These are good names in physics, and the others are very good names in probability. All are very good in both fields. It's a very interesting story where parallel, the same problem came up first in physics, later in few years later in mathematics, without knowing about each other. So the mathematicians, when they started to write these James Norris and Chris Rogers, David Williams, these are leading people in stochastic analysis, see a couple of years later than 83, 4 years later than Durrett and Rogers, 5 years more, and so on. They didn't know about the physics papers, no reference to them, but seemingly the same type of problem came up. Of course, the questions were put in different ways. So it's an interesting story in this sense. And here are some conjectures which were formulated mostly in the physics papers. Of course, when you read a physics paper, they don't say that they make conjectures. They speak about facts. But in our terms, these are conjectures. Namely, that if you take this type of process, actually it was concrete examples in the physics papers, then in one dimension, in low dimension, you expect super diffusive behavior, as of course you would expect, but because in low dimension you are more recurrent anyway, and you feel more of your own past behavior, and certainly if it differs from diffusion on the long time scale, then it must be super diffusive because it's pushed away from locations where you had been. So it's not so surprising that it's super diffusive. What is a bit surprising that from non-rigorous but very beautiful arguments, scaling arguments, it drops out what to expect, that in one dimension you expect time to the 2/3 scaling of the displacement, and though for those of you who are in this KPZ story, this 2/3 is not by chance. So it's somewhat, I don't say, okay, so it's not unrelated. It's not totally by chance, this 2/3. And the limiting distribution, if okay, I'm not able to, yeah. And the limiting distribution is something unusual. So that comes out from the scaling argument, which is not a rigorous one. In 2 dimensions, which is the marginal dimension for recurrence, as we know, and it's the marginal critical dimension for this story too, because recurrence is important here. You expect, or they expect, or the conjecture goes that it's like diffusive, but with some logarithmic correction. With some logarithmic correction, with gamma being some, that zeta, this exponent zeta being something positive, so it's some logarithmic marginally super diffusive. And in 3 and more dimensions, these scaling arguments would suggest that it behaves like diffusion. So in the long time scale, a central limit theorem holds. And yes, so with diffusive scaling. Now, even, okay, I can tell you that these are very difficult things. So in the last one, you would say, okay, central limit theorem, we have seen central limit theorem so many. But the central limit theorem is a difficult thing if you don't have sums of independent or weakly dependent random variables. Good. Here are some results. My work in all this story, all this long memory thing started with this paper published in the Annals of Probability in 1995, when for a particular example of this, for a particular model on the lattice, discrete time, discrete space, I was able to prove this time to the 2/3 scaling and identify indeed the limiting distribution, which is a very strange thing indeed. I'm not going to speak about this is an old stuff. For those interested, I can give you, okay, you find the reference, but I'm happy to speak about it. I'm not going to give details because it's not a fresh stuff. It's very beautiful in my opinion. Sometime later, not much later, about the same years, we started to work with Wendell and Werner about okay, what the limiting process would be. So if from my paper, the one-dimensional marginal, so the limit theorem dropped out, with some more work with the same method as in that paper, the finite dimensional marginals drop out. But it's difficult to guess what the limiting process would be because it's not one of these usual things we learn in probability like I don't know, stable or Levy process or that. Where we constructed this object, and in that paper, actually, just for the record, in this paper, what today is called the Brownian web, and many of you have heard about it, is actually constructed in this paper. We didn't call it that name. Later, other people gave that name anyway. But the Brownian web includes, so it's the process is constructed as a derivative or derived from the Brownian web in a sense. And much later, we were able to prove with these co-authors, Pierre Tarrés and Benedek Walko, we were able to prove super diffusive bounds on the variance. In general, mind that here the theorem, this theorem is valid for a particular, some combinatorics is in there, and if you change the combinatorics, then some arguments don't work. But the physical phenomenon is the same, and you expect the same behavior. This is what we call universality, right? That big classes of objects behave in large scale the same way. For some particular combinatorially treatable cases, maybe you can do something, but you expect for the class. When I say robust, I mean analytic proofs, not relying on combinatorial details of the model, which work. And what you see here is a robust bound and super diffusive, as you see. So in the diffusive case, this would be 1. And what we expect in general is what? 4/3. Instead of a 4/3, we can prove a lower bound of 5/4, which is less than, nevertheless, it's good. And what's much missing here, a fully robust proof, an analytic renormalization group, rigorous renormalization group argument, fully rigorous proof of this behavior on the long range. Right? This is totally missing. There are examples, and there is a robust proof for bounds, upper and lower bounds, which do not match. But it's far from a limit theorem, far even from matching lower and upper bounds. So this is one set of results which exist, and I will probably speak maybe the details of this last one are very similar to what I showed you the day before yesterday about the super diffusive. This is easier, by the way, than the two-dimensional thing I showed you last time. Now, what happens in 2 dimensions? In 2 dimensions, this is exactly the same type of thing what I showed you the day before yesterday for that particular random walk or diffusion in random environment when we had the drift was the curl of the Gaussian free field in 2 dimensions. This is a different thing, a different object, but not unrelated to that. And the bounds you are able to prove are the same. And this is in one of these papers. The previous one is in one of the papers. The previous one, this one, is in one of the papers. You see a paper with these authors, which is in your booklet. And this one is in the forthcoming papers in your booklet, which is by these 2 authors. What we expect is t times square root of log t for the variance, but we are far from being able to prove that. And what is also done back in 2012 with 2 PhD students of mine is indeed the central limit theorem in 3 and more dimensions. Diffusive behavior, central limit. These statements, what I told you, are not rigorously stated now because I didn't give you conditions, and I will give because this is was just sort of introduction. Precise statements will be seen later. Now let's see what happens. Let's see what happens. Again, the basic philosophy is always the same. Travel with your random. These are random walks in random environment. In this particular case, the random environment will be this occupation, smoothed occupation time measure, or maybe the gradient of the smooth occupation time measure seen from the position of the random walker. So travel with the random walker and follow the environment. That's what we did in the random walking random environment, and that's what we do here. Just here the environment also changes in time, right? Now this is the good way to look at these objects. What we do is the following. We have a finite dimensional process, a d-dimensional process xt, which is strongly non-Markovian. We cannot put our hands on it. We trade it for an infinite dimensional process, which is Markovian. Because this will be the field is an infinite dimensional. So I define it now. So take the function space as you see here. So that means infinitely differentiable vector spaces over Rd are the elements of my space, but which satisfy the gradient condition. So they are gradients of something. That means that the line integral on any closed curve is 0 of the vector field. And I define some, yesterday I also did that, the day before yesterday I didn't write on the blackboard. Now it's cheap for me because I just do this and you see it. Some semi-norms on this space, namely take any partial derivative of any component and divide it by 1 plus x to the 1 over r is any integer, and this should be bounded. That means that any partial derivative should increase slower than any power. That's the point. Now these are semi-norms. You can make it a metric space. So this is an infinite dimensional metric space I'm in. I'm set myself in. And now let's go back here. What is this process? Travel with your random walker, and what you see here is the field of the gradient of the negative gradient of the local time. When I say negative gradient of local time, I mean smoothed out locally regularized local time, and seen from the random walker, but not only at the spot where you are. That would be just one vector. All. Which makes it a vector field. So that's my object, and this is the space it sits in. And my claim is that this is a Markov process with almost sure continuous sample paths in this infinite dimensional space. It's easy to convince yourself that if you know the whole picture, then what happens? You are pushed by the gradient and add Brownian noise. So if I give you then you know how to change it by shift and by adding a little local time locally. So that's a Markov process. And the analysis will be analysis of the infinitesimal generator of this Markov process on a proper space. So infinite dimensional analysis. Good. Now let's define some operators. For the moment, I define some operators. This will be unbounded operators, so you will have to be very, very careful how to define them. I'm not doing more than take any finite, smooth, finite dimensional smooth cylinder function, which means the following: functions of the field which are defined in the following way. Give me n points and tell me which partial derivatives of the field to look at, and my function will be only a function of these data. Smooth function of these data. Is it clear what I mean? So functions defined, which you don't have to see the whole trajectory. I give you 5 points, 5 ways of taking partial derivatives, and I say take this and that polynomial of those numbers which you get this way. Now on these functions, I can define clearly and easily the following operators, namely a sort of a gradient, which means the following. By the way, I didn't emphasize something which I go back and emphasize, I should have, that on this space, shifts are well defined. I mean spatial shift. A spatial shift, let's say tau x, tau z, omega at x is equal to omega at x plus z. So spatial shifts are well defined on this space, and continuous and they have all the trivial good properties. And what I'm defining here is the gradient in the infinite dimensional space, mind, of gradient with respect to these shifts. Take a function, as I told you, smooth cylinder, finitely depending smooth cylinder function, shift, okay, do this, but with a little in the direction j, E sub j is unit, subtract the original value, divide by epsilon. For these functions, the limit will exist because I said that these functions are smooth and so on. My field is also smooth, no problem. Define a type of Laplacian for these functions, namely the operative definition is what you see here. I could give you more highbrow coordinate independent definition, but that's good. And what's a different type of thing is what, for those who know some Malyavin calculus for later, it's directional derivative, or maybe, yes. Namely, take this function f, mind that the function f, I'm sorry, I have to go back. This f was a fixed function that comes with my model. F is the gradient of my smoothing v, right? And this operation is the following. Add to omega. Omega is my field. If to omega I add epsilon times this function, this is again smooth decay at infinity, no problem. I stay in the field, in the space, capital omega. Add epsilon times this and subtract the original one, divide by epsilon. So in the function space, I differentiate in the direction of f. Right? And if I take this, then formally computing the infinitesimal generator, which means not only formally, take as you do, unfortunately this is G here, and in the lectures I used L, but in these slides I have G, so let me call it G today. So G of f at omega be limit as epsilon goes to 0 of f of eta at time epsilon minus f of eta of I forgot to put here something. Expected value starting from the state omega of f of eta at time epsilon minus f of omega divided by epsilon. This is the infinitesimal generator, as you know, if it's defined. Now, for this particular function, you clearly see, can you prove easily that it is defined, and you find this expression. And I tell you why you find this expression for the infinitesimal generator of that process, the coordinate process, the environment process. Why? So what is the change in the environment in a small time? You are shifted by, so the environment is shifted by the motion, but you also add local time. I mean, you add gradient of the local time, because the gradient of the local time is my field. Good. Now shift, the first two terms come from the shift. This is from the Brownian motion part, and this comes from your local drift. What is the local drift? Is the field at the spot where you are. That means omega at 0. So omega at 0 is the instantaneous drift. Take the gradient in that direction of your function and multiply by omega at 0, and that's how you get. So the first two terms come from the displacement, and the last term comes from addition of local time. You added epsilon times a delta, say, right? Not quite, but for the local time, but you smooth it out. You add epsilon times f, epsilon times v to local time, and that means epsilon times f to the gradient of the local time. Subtract the original one, so it's very clear. This is the operator, and the operator makes perfectly. These are linear operators, well defined on this. I didn't speak about closing them in some Banach space and so on. I'm not yet there. Good. The next step is, and this is sort of a miracle, finding a stationary distribution of this process. I mean of the environment process as seen from the random walker. This is this infinite dimensional element of an infinite dimensional space. So finding a stationary measure for it will be identifying a stationary measure, identifying a probability measure on this infinite dimensional, on this function space, which is invariant, right? And it's a very, very beautiful thing which comes in, and that's why I speak about this here. Namely, that it turns out that, again, I go back to my function space, to this function space. On this function space, I can define a Gaussian measure. I define a Gaussian measure, and I can prove that it's concentrated on this space, right? And I tell you which Gaussian measure is that. So the stationary object will be a Gaussian process with explicitly given covariances, zero mean and explicitly given covariances, which is a miracle. And namely, what you see is, you see it here, so it will be zero mean, and its covariance will be covariance matrix between spatial position. It's clear what I mean. So take the case component at the position x and the else component, because these are vector fields, at the position y. It will be, this is the green function, delta inverse is the green function of Brownian motion of the Laplacian, which in 3 and more dimensions, it makes the green function, as you know, the green function. In 2 dimensions, you have to be careful, but mind that we take derivative, and the derivative of the green function, it makes sense. That's why I take derivative. The green function itself would make sense in 3 and more dimensions. In 2 dimensions also, but you have to be careful, pin down things. Anyway, so take the green function as you learned it in high school, convolve it with this v, with this e to the minus x squared. You get something which is a nice object, and take the mixed partials and call it k sub that. What you see, it's easier to write down its Fourier transform. Its Fourier transform will be the KL component. K and L go from 1 to d. Its Fourier transform will be as you see there. And here you see why I said that's important, that function v better have a positive Fourier transform. So better be positive definite, otherwise this does not make sense. Otherwise, it's very interesting, and I'm not able, okay, I'm able to explain with some hand waving, but not deeply mathematically understand that if I have this type of, if I have this type, this is my v. Right? And this is another v. I don't write formula for that. You don't see much difference except that I'm not right. Maybe this looks much more like that. Anyway, but this looks exactly the same, but its Fourier transform is not quite positive. That's not good. But physically, that's not good because it doesn't give you a covariance. It doesn't give you a stationary measure. I have some explanation for that, but I don't enter into that. So what is this, what you see here again? This is the gradient, this is the covariance of the gradient of the Gaussian free field. Just the Gaussian free field on its own is not a field, it's a generalized function. So you have to smooth it out and then take. So it's a local regularization, or take local regularization of Gaussian free field and take now the gradient. Recall that last time when I spoke about that random walk in random environment, it was the curl of the Gaussian free field in 2 dimensions. This is the gradient, so it's not the same thing. It's not the same thing. So the stationary measure of this process will be take Gaussian free field, locally regularize it, and take the gradient of that, what you get, and that distribution will be. And I have 2 proofs of this. Mind, let me again emphasize something. It doesn't mean that my process eta t is a Gaussian process. At fixed time, the distribution is Gaussian. At different times, jointly is not Gaussian. It's exact. Why is it so surprising? But if it was Gaussian, it would be trivial. Then I would compute everything explicitly with my digits, no? But this is exactly the difficulty in all these type of problem in SPDE. So if you look at KPZ, there are some KPZ specialists here. So the KPZ, the stationary measure, when it makes sense, is white noise, is Gaussian. It's a Gaussian, but at two different times. Jointly it's not Gaussian. Am I right? Am I right? Same thing happens here. Good. I say miracle, but I mean miracle, because it's not complete. It's not difficult to prove once you guess. It's not difficult to prove, but it's some sort of interesting thing. Let's prove it if I have time for that. When do I have to? How is there any organizer around? Yeah. So what is supposed that I started at past, and how much time I have altogether? Sorry, 1 hour. At 45. Oh, I have time. Okay. Okay, so let's prove this, or let me sketch you the proof, which is there are two proofs. There are two proofs, and in two different papers you find the two different proofs. In the one is by Ito calculus, and the other one is functional analytic. I will show you the Ito calculus proof now, which I like. I like both, but first of all, let me explain my notation. So these are U and eta, these are vector fields over Rd. U is a test function, and eta is my random field. Yeah? And when I say uk eta k, when I say uk eta k at time t, I mean sum over k from 1 to d integral on R d ukx eta kx dx. Right? U is a test function, whatever test function. And eta is my process. I want to prove something about my process. Good. So I take this. The process is an infinite dimensional object. I don't know what to do with it. So take better a number, take its scalar, so test it with a test function. You get a number, which is a process, for which you can apply Ito's formula, because it has the properties of it's an Ito process. Apply Ito formula. You know how eta changes in time. Eta changes in time by shift, which comes from a deterministic part and the Brownian part, and by addition of local time, right? Now, there are dB. By shift, what do you do? Differentiate eta, which is a differentiable function, apply dB, differentiate in the L direction, apply dBL. Here there is a scalar, what is an integration by parts, derivative is put on the other side. But you also have to add the Ito term. The Ito term coming with this one is second derivative. When you see double, by the way, when you see double indices, you sum over them. Yes, whenever you see two indices, you sum over them from 1 to d, right? So these together are the Ito differential coming from the dBt term. Derivative with respect to space and dB plus 1/2 second derivative with respect to space, some dt, right? You have another dt term coming from the drift. The drift is what? The local value at 0 is the vector which is the velocity vector, right? And you are shifted, you are drifted by that much. Eta L is the L's component of eta 0. And what happens? All eta is shifted. That means take spatial derivative of eta within that integral and do it. That's what I did. Just I pushed the derivative on the other side and I got a minus sign. And I have yet another part, namely that to eta you add a little bit times the derivative of v. And it's written there, you add a little of the negative derivative of v, negative gradient of v. F was negative gradient of v. So you have a negative gradient of v here, push it on the other side. V is a fixed function, is there on the blackboard. This is the Ito, this is the infinity, this is Ito's formula applied to this to that object you see on the left-hand side. Good. That's simple. Now, what I want to prove is the following. Let me give you what I have in mind, because otherwise it's just trying to find something in the dark. So I prove the following. I want to prove that d by dt expected value of e to the u eta t is 0 for all test functions with respect to some measure. If I prove that this is true with respect to some measure, what do I prove? That the moment generating function, maybe I put an I there. I don't put an I. I could put an I. Moment generating function doesn't change with time. No matter what u is, that would mean that this measure is invariant. If I can prove this thing, I can prove this measure is invariant. So I do this in the following way. Okay, but what is the measure? First you have to guess what is the measure. So I make an ansatz. I make an ansatz that my measure is Gaussian. I want to try a Gaussian measure with zero mean and some covariance. And when computing this, and I compute this with two steps, namely first conditional on ft and then expectation, and I will play with this dt, I push it in and out because u is everything is smooth, right? Anyway, I make an ansatz for a Gaussian distribution. I make this equation and I find a closed equation. That's the miracle, that I find a closed equation for the second moment, right? It's not the case always. So this is indeed a coincidence of things. I will comment on that. Good. And what you see is the following, starting with the Ito formula up there. I write down the Ito formula for the exponential, which is, once you have an Ito formula for the Ito process, for the exponential it's trivial how to transfer it, and compute the conditional on ft. And what do I do? Yeah, that's that is. Let me see what I do. Yes, that's just use of this and use Ito for the exponential function. Nothing done there. And now I make the ansatz. Let's assume that eta is Gaussian. Let's assume that here I only have the one dimension. That's important, that I only have the one-dimensional distributions. I mean one-dimensional in time. Only one-time distributions. Let's make the ansatz that it is Gaussian. And if it is Gaussian, now I should have to explain all these. So you write down, that is a Gaussian with a covariance. I didn't write down the covariance. Ah, yeah, there is it. With some covariance there, which is to be determined. Right? And I do the computations. I go back once more. Note that I have up to this is linear in my field. Okay, it's an exponential anyway. This is linear in my field. This is quadratic in my field. Eta is there and eta is there. Those are the Gaussians. This is quadratic in my field. And this is just this is constant. Right? And the only formula you have to use is the one about if you have, and by the way, what you have in the exponent is also Gaussian. These are joint Gaussian, different joint. I have three types. So the most complicated expression in this object is e to the x times y times z, where x, y, and z are jointly Gaussian. Right? And for this we have formulas. That's why we love so much Gaussians, because closed formulas, everything can be expressed in terms of second moments. Right? So do what you have to do. Let me not make these are elementary computations once you arrive here. And you get a closed, you have a closed form, indeed you get a closed form for C, which was supposed, and what you get is the following, you get that K, I told you. You may add another covariance function to it, which is a curl field of possibly another Gaussian. So you can have the most general thing you can have is take two Gaussian free field at one hand, another Gaussian field so that these two are jointly Gaussian, maybe the same. And K sub K is the gradient of the Gaussian free field, and D sub KL is the curl of the other Gaussian field. So this is just that I could combine the two models which I spoke about the day before yesterday and this one, but I will not. So the not most general case is that I take this 0, D equals 0, and I got my stationary measure. Right? I got my stationary measure, which is Gaussian with this covariance. Good. And yes, I will make a remark on the lattice case in a moment. What I want to say that at this moment, I have the process on an infinite dimensional function space. I have a Gaussian measure on an infinite dimensional function space, which, by the way, is also something close to our heart because it's related to the Gaussian free field. And then I will go to the L2 space over that object, the Hilbert space, and I will do analysis on that space, which will be sort of Maillard type of thing. Good. Now let's go to the lattice, because this was all done in the continuum space. Let me go to the lattice and make just some comment, because I gave you models on the lattice, which are, in one sense, technically easier in the sense that you don't have to care that much about the operators, mostly are bounded and are simpler. On the other hand, doing analysis on the lattice is always more may cause headache. But I make a comment. So if you do the same thing for, say, the second model, continuous time, the second one I mentioned at the beginning of my lecture, continuous time, self-repelling random walk on ZD, then the stationary measure do exactly these type of things, but you will not have Gaussian computation. You will have to do some Gibbs conditioning and so on, except in particular cases. In particular cases, Gaussian, but in general, no. And the stationary measure will be a Gibbs measure for the so-called gradient model. And let me not enter into much detail. That means that your variables are given on the edges of the lattice, which satisfy the gradient condition. You have a Hamiltonian, as in Hugo's talk was using Hamiltonian, but here you have a Hamiltonian like that, where capital R is the primitive function of the odd part of my W at the beginning. And I need this capital R be strictly convex, and that's why I need R be strictly increasing, right? And then I have well-defined this Gibbs measure. That will be the stationary. If it happens that R of U, the odd part of the W function, is exactly linear, then this will be the gradient of discrete Gaussian free field on the lattice. The field itself will be the gradient of discrete Gaussian. And again, on the lattice I could do, and actually I do in the paper, the same things, but time is short, so I'm not going back. So I go back to the continuous object now. So I have a Hilbert space, which, mind, the Hilbert space is L2 of omega pi. Omega is the explicit vector space, the Fréchet space, and pi is the Gaussian measure on it. So it's not an abstract object, it's a very concrete object. And as I told you yesterday, a Gaussian Hilbert space is graded naturally. There is a gradual grading. By grading, I mean that the Hilbert space builds up as some orthogonal sum of Hilbert spaces. And the zeros one is a trivial one. It just contains the constant function. It is one-dimensional, but the rest are all infinite dimensional. The first one are all linear combinations of my Gaussians. The second one are all quadratic expressions of my Gaussian orthogonalized to the first subspace. The third one are all cubic expression, up to cubic expression, but orthogonalized to and so on and so on. And now, going back, I had an expression of the infinitesimal generator. Remember, there was an expression which consisted of shifts of Laplacian, of shifts of some multiplication operators, and of directional derivative. now I go to my Hilbert space. Those functions are densely there in my Hilbert space. Those functions for which those operators were defined, that means functions which depend smoothly on, so finite cylinder functions, what I called, those are densely there in my Hilbert space. So the operators I wrote down and I explained to you are acting on my Hilbert space, at least in a dense subspace of my Hilbert space. Now some miracle comes, which I'm probably not able to explain it here, but this is standard in a sense, that in L2, in Gaussian Hilbert spaces, you can do computations. You have these multiplication operators expressed as annihilation operators and creation operators. And one more element is here as compared to last time when that didn't appear, that this directional derivative operator, I speak to those who know some Malevin calculus, I don't know if there are some. The directional derivative operator also has some special form, right? And if you put together all these things, then you arrive to the infinitesimal generator, a form very similar to what I've shown you last time, but the meaning is not quite the same of the operator. I mean of the creation and annihilation operators. Laplacian is the same as it was the day before yesterday. Gradients are the same as it was the day before yesterday. Multiplication formally is the same, but mind that these omegas, as opposed to what was last time the case, that the omegas were curl, had another symmetry somehow. So the omegas are gradient fields, as opposed to 2 days ago when a similar formula appeared in another context when the omega were curl. So it's not, formally looks the same, but it's not the same thing, right? And in terms of these weak polynomials, which I explained 2 days ago what they are, you see here the definition of the operators. So this makes perfectly good sense. This operator you see there is unbounded on the Hilbert space, but it's controlled, it's well understood, right? In particular, the delta, the Laplacian, keeps the grading. This part lowers the grade by 1, and this part raises the grade by 1. You can see it here, right? And what happens next is apply analysis on this space. This is difficult. Okay, I will not show you all computations because it's not instructive. It's instructive, but it's instructive if you do it yourself, not if you see on a screen. So I just give you ideas. Again, we do exactly what as I started my lectures more than a week ago, that you write the displacement as a sum of a martingale and an integral over the trajectory of this Markov process, where the Markov process is eta s, which I explained already well in much detail, and the function phi you have to integrate is a very simple looking one, namely phi of omega is omega at 0, right? But you have to integrate this along the trajectory of the, and what is here done, probably I could skip because I explained it in my introductory lecture. So let's, and here is the theorem. Here is one of the theorems. One of the theorems is the following, that under these conditions, the limiting in 3 and more dimensions, and starting from the stationary distribution, from the stationary setup, that's very important. Mind that in my first slide, I said that, okay, let's take this L, which I denote by this lowercase l, the local time, but let's initiate some initial value. And it did not make sense at that point. Why do I add initial value to the local time? Because I want my process to be in the stationary state. And if I want it to be in the stationary state, then I have to start somewhere. Now, this sounds like a harmless statement, but it's not that harmless, as I say. Because what you add is not a positive, it's something which, it's a Gaussian, which is not the gradient of a positive function. So you don't initiate with a local time, you initiate with something which could have negative values, and thus have negative values, because it's in equilibrium, and the equilibrium is like that. And then the increments are the local time. Right? This is the stationary state of the process. And so I start from this stationary initialization, and the statement is that the process does have a limiting variance. So the variance divided by t of the displacement divided by t does have a limit, which is not automatic in non-self-adjoint cases, right? It's part of the problem. And moreover, I have lower and upper bounds on the variance, and I have central limit theorem for the finite dimensional distributions, the converging to the joint distributions of the corresponding Brownian motion or Wiener process, but I don't have tightness. So I don't have convergence of the process. It's maybe a nuisance only, but anyway, it's technically always a headache, causes headache, and I didn't spend much time with that. So that is the theorem. And there are similar theorems for the lattice case. A similar theorem for the lattice case, but for the lattice case in very particular, I don't have a general theorem for the lattice case. Only I have, for the lattice case at the moment, I have a theorem only when the odd part of the function w is linear. So when the stationary measure is the Gaussian free field, because that I can do some computations which I can't do in other cases so far. And the other theorem is this one about the because these two theorems are valid in 3 and more dimensions. As I told you, in 1 dimension I have my old and other old results exist, which prove robust superdiffusivity. Robustness has power law superdiffusivity. In 3 and more, here is the central limit theorem with diffusive scaling. And in 2 dimensions, there is a marginal superdiffusivity. We expect more, but are not able to prove more. And again, a warning that it's not quite so. Take the Laplace transforms of all 3 terms, and the inequality holds for the Laplace transforms, not for the functions themselves. Good. I moved too much away. Probably you can't see me, but I just realized. Good. Sorry. And the method of proofs, now it's just recapitulation of my first lecture, actually, or my second lecture, not the first one. That in the diffusive case, I use these non-reversible extensions and improvements of the Kipnis-Varadhan theory, in particular the so-called graded sector condition, which I mentioned, but it's very, very technical, so I will not go into details because with less than 15 minutes left, it doesn't make sense. And the superdiffusive bound is proved, as I showed you 2 days ago, using this Landim-Kostel-Zalmhofer-Yau type of approach, but it's much more involved because the variational problem we arrive at in 2 dimension, at marginal case, it's difficult. And this is something which I told you in the first lecture, so I don't go through it. And this is about the graded sector condition, which doesn't make sense that in the last 15 minutes. So anyway, what I need, I just tell you something, what I need to control is a bound on the norm of what? In this space I speak about. Laplacian to the -1/2, this raising operator, which consisted by a gradient and a raising operator, and Laplacian to the -1/2 applied again. This is an explicit formula. This gives an explicit formula in this particular case, an explicit computation. You need to bound integrals and so on, and it turns out that indeed is bounded by something increasing sufficiently slow that the series of the inverses be divergent. Actually, if I'm not mistaken, it will be of order 1 over square root of n. I mean of square root of n. Cn will be of order, or n to the 1/2 plus a little, something like that. That's what I do. So you are well within the range when my theorem holds. And what I wanted to tell, this is all true only in 3 and more dimensions. So in 2 dimensions, for various reasons, I have the super diffusivity, but in particular, okay, there are some computational details which are subtle and only in 3 or more dimensions hold. This is here, is n to the 1/2, yes? And the rest is something similar to what I told you yesterday. So I'm with 15 minutes left. So I think I stop here because the rest would be very technical and doesn't make sense in the last 10 minutes to enter in technical details. So I should make some summarizing comments. So what I've done in this last 10 days is, first of all, I think that the models I considered are not just mathematical gadgets, are motivated by physical problems. So random walk in random environment, homogenization, we have heard yesterday, it's very similar, it's another side of the same coin. These are important problems coming from physics, not only from mathematics. These problems lead to understanding the diffusive or super diffusive behavior of this type of displacements. The 2 kinds of processes which I considered in the end was random walk in random environment, but not among random conductances. So not self-adjoint. That's the main message, that I did non-self-adjoint cases, and the main difficulties came from the non-self-adjoint cases, right? And we proved quite a general central limit theorem for that case, and similarly for this random walk with self-repellence. There are other models which I didn't have time for, and I think I stop, and I thank you for the attention. And